In buildings, maintaining visual comfort means ensuring that people have enough light for their activities. The light has the right quality and balance, and the people have good views. In this lecture, we are going to discuss about vision and photometric units, daylighting factor, glare and quality of light sources. What we call light is the part of the radiation that sun sends to earth, that our eye perceives, and corresponds to about half of all the solar energy that reaches us. The range of wavelengths to which our retina is sensitive is comprised between 380 and 780 nanometers. Within this interval, at each wavelength, we attribute a color, but our eye is not equally sensitive to all colors in terms to wavelengths. It is little sensitive to blue, violet and red. Y is highly sensitive to yellow, green. Good lighting should be based whenever possible and appropriate on natural light. Of course, supplemented when necessary by artificial light. In order to talk about light, we have to introduce the fundamental measuring units, which are the first one, luminous flux. The unit is lumen. This quantity indicates the amount of luminous energy emitted per unit of time from a source. For luminous energy, it means radiant energy emitted in the range of 380 to 780 nanometers. The second one is luminous intensity. The unit is candela. A light source emits its luminous flux usually in different directions and at different intensities. The intensity of light radiated in given direction is defined luminous intensity. The third one is illuminance. Unit is lux. This is the ratio of the luminous flux received by a surface to the area of the surface itself. It indicates the amount of light that strikes a unit area. The fourth one is luminance. The unit is candela per square meter. It is the ratio of the luminous intensity emitted by a surface in a given direction to the apparent area of the surface. That apparent area is projection of the surface on a plane normal to the direction considered. Clearly, the luminance varies according to the source. Some examples are shown in the table. The illumination levels instead varies not only according to the source, but depends on many factors, including the surface itself. Another important parameter is the daylight factor, DF, which is a measure of the amount of daylight available in a space. It is defined as the ratio of the illumination of the working plane in a given position to the illuminance that would be under identical conditions of time and place on a horizontal surface exposed outdoors so as to receive light from the entire sky with no direct sun. The daylight factor depends on the window's dimensions, the room depth, the shape, location and type of windows and shading devices, the obstruction provided by the contacts, the color of the internal and external surfaces, and on the position in the room. The figures show an example of the variation of daylight factor in a room equipped with a window. The mean daylight factor DFM of an enclosed space is defined as the mean value of daylight factors measured at the level of working plane by a grid of sensors extended to the whole space. It can be estimated with this formula, where tau, which is visible transmittance of glazing, theta is the sky angle, A glazing is net glazing area, A total is the total area of all interior surfaces including windows, rho m is the mean surface reflectance weighted on area, and generally it can be taken as 0.5 as the first approximation. In the tables, some example of recommended values of daylight factor are shown. Along with daylight factor, another parameter is daylight autonomy, which is defined as the percentage of the building occupation hours in which the required minimum level of illuminance can be maintained with the natural lighting alone. As regards to glare, the definition according to the standard EN 12464-1 is the visual sensation produced by surfaces which produce high luminance gradients within the field of view. The direct glare depends on the characteristics of the space and of sources, either natural or artificial, directly in the visual field of a person. The reflected glare is caused by shiny surfaces reflecting in the eyes the image of light sources, and it happens when the incident angle of light on the horizontal work plane falls into the view angle of the observer. To assess the level of glare, an index was developed, the Daylight Glare Index (DGI). The DGI allows predicting the glare due to the natural light through the index UGR, which is Unified Glare Rating, is used also for evaluating the glare due to an artificial light source. Based on the resulting values of DGI, the level of glare can be evaluated according to the classification shown in the table. The human eye has difficulties to handle high level of luminance directly in the area of vision, which falls in the fovea. As the source of potential glare moves towards the central area of the visual field, the allowable luminance level decreases as shown in figure. Then, the closer to the center of the visual field, the more light sources are potential sources of glare. In the figure, the sources are progressively more problematic from A, no problem, gradually to B, C, and the windows, causing glare. Some potential sources of glare and recommended reflectance values are shown in the figure. The color temperature is a parameter used to individuate and categorize in an objective way the color of light from a light source compared to the sample source, which is black body. To say that a lamp has a color temperature of 3000 Kelvin means that the black body at this temperature emits light with the same emission spectrum. The light sources are divided into three groups depending on the color temperature as shown in the figure. From 3000 to 3500 Kelvin, warm white color. From 4000 to 5000 Kelvin, neutral white color. And from 5500 to 7000 Kelvin, cool white color. The black body is the reference by which one judges a light source that emits in a similar way as shown in figure. Flame and incandescent lamps, for example, have a continuous spectrum. The spectrum of a discharge lamp, mercury vapor, fluorescent, or of a LED lamp, instead is different in shape from that of a black body. Light sources with a low color temperature help to create a warm environment if the lighting levels are low. A pleasant lighting of the interior is obtained with the light sources having a color temperature not higher than 3000 Kelvin. The color temperature for some sources are shown in the figure. If the general level of illumination exceeds 500 lux, it may be preferable to use 5000 Kelvin sources. Sources with higher color temperature, when used with lighting levels below 500 lux, create an atmosphere cold and unpleasant. High value of color temperature should be associated with high levels of illumination. That is what happens with natural light outdoors. Finally, the color rendering index CRI is a quantitative measure of the ability of a light source to reproduce the accurately colors of objects by comparison with an ideal source up to 5000 Kelvin or daylight above 5000 Kelvin as shown in the picture. In conclusion, while designing the sustainable buildings, these parameters must be considered for visual comfort of the occupants.